Okay, this video is going to show you how to perform simple mantle melting calculations in the presence of sulfides. This is adapted from the approach of Lee et al. 2012 and my paper from 2019. So as normal, you're going to go to the Read the Docs page and you're going to click on the left-hand side under this heading Mantle Melting. And we're going to do the most simple example in this video, so that's the top one. Again, you're going to click Download View in NB Viewer and you're going to press the Download button here. This will then go into your downloads and you should be able to move that file into whatever folder you want to work in. So I have navigated to where I put this. I will do that just quickly now. So I put this in the examples mantle melting folder and you just double click on it and then it opens it. So first thing you're going to do is Shift Enter and you need to make sure you have PySolveSat installed. If you don't, please go watch the introductory video about how to do that. And if you installed it a while ago, you might want to check your version. And then you can always communicate the version with me and that helps me find errors. So the first thing we need for mantle melting is an estimate of the silicate melt mode. Now, many of you know that this will change during melting. However, when we're modelling highly chalcophile elements like copper, the KD in the sulfide greatly dominates. So actually it doesn't really matter whether this is constant. And if you see it in the supporting spreadsheet of Lee et al., they do keep it constant for their example. So this is the most simple example. We're going to keep it constant. There is a more complex example where I show another option. So we're saying we have 60% olivine, 20% OPX, etc. You then need to enter your KD values for each element. So here we're doing copper and we're going to say olivine is 0.048 and then crucially sulfide is 800. So this is really, really dominating, which is why these modes don't matter very much. So then we're going to use the function SS Lee Wieser sulfide melting. So the first thing we need to tell the function is the modes. So that's the proportions up here. We need to tell it the KD values we want to use. So that's these. We need to tell it how many iterations we want to do. Now, this model basically does batch melts, but if you make the step small enough, it's basically like, the fact that that's batch melting doesn't really matter, and you're aggregating those small batch melts. There's more detail in the manuscript about how that works. You need to pick a sulfur content in ppm of the mantle. So here we're going to use 200 ppm. You need to pick a content of sulfur in the sulfide in ppm. So here we're choosing 33 weight %. And then you need to pick the SCSS in the melt. And again, this is a simplification that I'll talk about in a later video, but say we assume that the mantle melt can dissolve 1000 ppm sulfur. Finally, you need to say the amount of the element, so in this case we're modelling copper, that you can dissolve, that is present in the peridotite before melting. So here we're saying 30 ppm. And then finally, you can also select a proportion of sulfur 6+. So this is the amount of S2- that dissolves, so this would scale it up. And there's another video about how to perform these corrections. So what you can see it outputs is it outputs the F, which is the extent of melting. Just going to take a second. It is doing 3000 iterations. You can make this significantly faster by doing, say, 100 or 200. So this is the amount of melt. This is the mass of the residue. You then have the bulk KD of copper, and then you have the amount of copper in the aggregated melt. You have the amount of copper in the instantaneous melt. You have the amount of copper in the mantle residue. You have the amount of sulfur in the mantle residue. You have the amount of sulfur in the instantaneous melt. The amount of sulfur in the aggregated melt, and the fraction of sulfide in the mantle source that remains. So we can also do this for an incompatible element like barium. Say we want to model the contrasting behaviour of copper and barium. Now obviously at this point the assumption of modal melting gets a little bit dodgy, but it doesn't really matter because it's so incompatible still. So here we're choosing different KDs and we're saying there was 6.85 ppm barium in the mantle before melting started. Everything else is the same. So that's going to run. And then what we can also do is we can perform calculations for different sulfur contents. So here we're going to, instead of using 200 ppm, we're going to use 100 ppm, and here we're going to use 300 ppm. And this will just give you an idea of how the different copper against melt fraction matters depending on the sulfur content. Obviously more sulfur in the mantle, more sulfides, higher bulk KD for copper. Okay, so now we're going to make a plot to show this data. So we're going to do two subplots. What we're going to plot to start with is this 100 ppm scenario. We're going to plot the melt fraction F against the aggregate amount of copper in the melt, so aggregated melts. And then we're also looking for the point at which sulfide is exhausted. This is very interesting to us. And we can do this by using the numpy where function. So we're looking for the closest point where the amount of sulfur in the residue is 0. So that's the moment you exhaust mantle sulfides. This is then a series of true-false statements, and by doing the data frame column .lock this thing, it will basically pull out the value where this is the case, so where that 0 point exists. We're doing the same for 200 ppm, 300 ppm for copper, and also plotting barium on top. And this is what it looks like. So you can see you have copper versus F and barium versus F. You can also change the silicate proportions. So here we're reading from an Excel spreadsheet that does have changing proportions. This is like if you were to drag things down in the Lee spreadsheet. So you can have a look at this. So you can see that the amount of olivine is increasing and the amount of clinopyroxene is decreasing. So this is a more realistic scenario. So now instead of feeding in a single value into the mode's data frame, you are referencing this column. So this is all I is the amount of olivine, CPX, etc. Again, we then feed this into the function. Ignore any of these pink. Oh, yeah, you can ignore this. This is basically saying you've inputted a data frame of silicate modes that doesn't match the number of steps you asked for. We are changing the number of steps to match the length of your data frame. Right, so you don't want to ignore this. Basically, what this is saying is you're telling it to run 1,296 melting steps based on those silicate modes. But here you've set n is 3,000. Now, it's not going to use this value because this one makes more sense. It doesn't know what modes to use for the other 1,800 steps that you don't know about. So at any point, it will overwrite it. So in general, read these pink warnings. If they just say like deprecation warning, ignore them. But this is specifically a warning we're coming in. And then you could plot this stuff up and have a look at it like we did with the previous one.